So when we did the standard multiplication algorithm, at the end of our problem, we counted the total number of digits behind our decimal. So we said there was one digit behind the decimal in our first multiplication, which was the 7. There were 2 digits, the 3 and the 6, behind the decimal in my second multiplication. So 1 plus 2 gives me 3 total. And so that's how I knew that my answer needed to have 3 total digits behind that decimal. So in terms of why that works, why I would just add up the total there of digits and that would be how many would be in my answer. We can show that using another method, and this is technically a method we should already know how to do because we've already gone through fraction multiplication. Since we know that decimals are really just special types of fractions, you can always take them back to fractions, right? And so if students struggle with fractions, this is not likely going to be their method of choice. But if they really understood fractions and they're struggling with decimals, they are going to love this. They're going to enjoy going back to fractions, and you can always do that. So what I'm going to do is I'm going to do the same problem, 85 and 7/10 times 2 and 36 hundredths, but I'm going to do it by basically rewriting both of those numbers as fractions, then do the fraction multiplication. And then once I get my answer as a fraction, then just change it back to a decimal. Since I started as decimals, it would make sense to go back to that. So this one, we can technically write that the same way we would say it, right? 85 and 7/10. So you could write it that way. If you do it that way, though, you're going to have to change that mixed number to an improper fraction before you can do your multiplication. So the more common way to do this is just to basically take the digits in that number and put it over your last place value. So in this case, the last place value is the 7 and it's in the 10ths place. So you would put that over 10. You would get the same thing if you had done this, right? 85 and 7/10. If I want to change that to an improper fraction, I would do 85 times 10, which is 850, and then I would add the 7 to that and get 857. But the fast way is just write the digits over the last place value. So same thing here, I could write this as 2 and 36 hundredths, the same way I would say it, since the 6 is in the hundredths place. And then you could multiply and add to get your improper fraction. But really, when you do that, you're just going to end up with all the digits in your number over the last place value. In this case, the 6 is in the hundredths place. So that would be over 100. And now I'm going to multiply these two fractions together. So this is going back to multiplying fractions. How do we multiply fractions? We multiply across. I would multiply my numerators and multiply my denominators. Now, 857 times 236, that I'm going to need to go off to the side and do. But technically, we really already did that, right? We did that when we did our standard algorithm. Matter of fact, when we went through our standard algorithm, we basically ignored the decimals all the way through and we multiplied as if it was 857 times 236. It was only at the end that we put our decimal in. So if we hadn't put our decimals in, when we did this with the standard algorithm, 857 times 236 turned out to be 202252, right? Or 202,252. And we didn't place the decimal there yet, right? And then there's, remember, shortcuts for multiplying by powers of 10 where we just attach zeros. So 10 times 1,000 would really, I'm sorry, 10 times 100 would be 1,000, right? 10, and then attach these 2 zeros. And so you really get 202252 or 202,252 over 1,000. And that's, 202,252 thousandths. And then we just want to change that back into a decimal. And so remember our shortcuts that we went through, dividing by 1,000 really just means you would move the decimal 3 spaces, since there's 3 zeros, right? 3 spaces to the left. And that's because there's 3 zeros, but that's also because, so really remember 10 is really the same thing as 10 to the first power, right? And then 100 is really 10 to the second power. And so 1 plus 2 gives me 10 to the third, or 1,000. So we're moving it 3 spaces, but really we're doing that because it's 10 to the third, or there's 3 zeros. So I move my decimal 3 spaces, or basically there's 3 digits behind the decimal, and I get the same answer we did before. And so this actually explains why that standard algorithm works. If you ever have a student ask why, go back to the fractions, right? So this whole idea of what we did in the standard algorithm, when we added, there was 1 digit behind the decimal and 2 digits behind the decimal, and we added 1 and 2 to get a total of 3 digits behind the decimal. That really comes from adding those exponents, right? Because this was tenths, which is 10 to the first power. This was hundredths, which was 10 to the second power. And when you're multiplying, you add exponents. So 1 plus 2 is 3.